Deep within the ancient rainforests of Borneo, a flash of vibrant color moves through the canopy. It is a creature of remarkable grace and astonishing agility. This is the red-legged langur, cloaked in a coat of soft gray fur, but distinguished by its striking maroon-colored legs. These primates spend almost their entire lives high above the forest floor, navigating leaves, branches, and dizzying heights. The canopy is a complex, three-dimensional world, a maze of pathways constantly shifting, breaking, swaying in the wind. It is an environment that presents a relentless series of physical challenges. For the langur, this world is a playground. We see it move with an ease that seems to defy the very laws of gravity. How do they do it? This is the central question that will guide our exploration. Behind that beauty lies a world of hidden physics and biomechanics. The langur is not defying gravity, it is mastering it. To truly appreciate the langur's mastery, we must familiarize ourselves with the language of physics that describes its movements. Let's start with three fundamental concepts: mass, force, energy. The langur's small mass, around 6 kilograms, is a huge advantage. According to Isaac Newton's second law of motion, force equals mass times acceleration. To understand the langur's incredible abilities, we must first look at its fundamental design. Its body is a blueprint for acrobatic excellence, shaped by millions of years of life in the trees. The red-legged langur is relatively small and slender, a build that is crucial for its arboreal lifestyle. This lightness is a significant advantage. Less mass to propel through the air, less force to absorb upon landing on slender, flexible branches. The true engine behind the langur's spectacular leaps is its legs. They are disproportionately long compared to its arms, a clear indicator of a jumping specialist. These long limbs are essentially biological levers. Physics tells us that longer levers can generate greater speed at their end. The langur's thighs are packed with powerful extensor muscles composed of a high proportion of fast-twitch muscle fibers, designed for rapid, forceful contractions. If the legs are the engine, the tail is the guidance system. The red-legged langur possesses a tail that is often longer than its body. This long tail serves as a crucial tool for maintaining balance on precarious branches and in midair. This is governed by a fundamental principle of physics, the conservation of angular momentum. The langur can trade rotation between its body and its tail. Power and balance are useless if the langur cannot securely hold on. Its hands and feet are beautifully adapted for the job, covered in thick, leathery pads ridged with fingerprints. These ridges increase the surface area of contact with a branch and help to channel away water, ensuring a secure grip even in the wet rainforest. By curling its fingers and toes around a branch, the langur applies force from multiple directions, concentrating this force onto a small area and increasing the resulting frictional force. The decision to leap is a complex calculation made in a fraction of a second. The langur assesses the distance. It gauges the wind. It checks the sturdiness of its launch pad. It sizes up its target. It begins with a deep crouch. The langur folds its long legs, bringing its knees close to its chest, storing elastic potential energy. The launch itself is an explosive, coordinated extension of the entire body. Powerful thigh muscles contract with incredible speed, straightening the hip and knee joints. If a 6-kilogram langur accelerates to a takeoff speed of 8 meters per second in just a quarter of a second, the force required is nearly 200 newtons, more than 3 times its own body weight. The angle of takeoff is crucial. The langur must adjust its launch angle accordingly, demonstrating an intuitive understanding of ballistics coded into its brain. Once airborne, the langur becomes a living projectile, its path tracing a graceful curve through the air known as a parabola. During this flight, there is a constant interplay between its kinetic energy and its potential energy. As it rises, kinetic energy is converted into gravitational potential energy. The langur adopts a specific posture to optimize its flight, extending its body to create a long, streamlined shape that minimizes air resistance. The flight may be graceful, but the landing is a controlled collision. All the kinetic energy the langur built up during its leap must be dissipated safely in a fraction of a second. The langur's body is a superb shock absorber, The instant its limbs make contact, it allows its joints to flex deeply. Ankles bend, knees bend, hips bend, acting like the suspension system in a car. The energy does not simply disappear, it is converted. As the limbs bend, the muscles do negative work, converting the kinetic energy of the fall into heat within the muscles. The first point of contact is usually the hands and feet. The friction from the leathery pads immediately begins to slow the langur's forward momentum. The langur has mastered the art of sharing the load, distributing the violent forces of impact across its hands, limbs, spine, and even the branch itself. It is a whole-body solution to a whole-body problem, executed with an elegance that conceals the violent physics at play. Life in the canopy is a perpetual balancing act. For the red-legged langur, every branch is a tightrope, and a fall can be fatal. Its ability to maintain balance is physics in action, specifically the management of its center of mass. To stay balanced, this point must be kept directly above its base of support. The langur actively manipulates its body shape with fine-tuned adjustments, extending limbs, shifting its torso, repositioning its center of mass back over its feet. The langur's most dynamic balancing tool is its long, elegant tail. The key principle is torque, turning force. When the langur starts to tip, it creates an opposing torque by moving its tail in the opposite direction. We see this most dramatically when a langur is surprised or loses its footing. In these split-second moments, the tail whips into action, often turning potential falls into recoveries. Rapid tail rotation generates gyroscopic force, resisting changes in the langur's orientation. The spinning tail behaves like a gyroscope and stabilizes the body. One of the most fascinating aspects of the red-legged langur's biology is the apparent contradiction between its high-energy lifestyle and its low-energy diet. Langurs are folivores. Their diet consists primarily of leaves. The answer is its highly specialized digestive system. The langur has a complex, multi-chambered stomach that is essentially a fermentation vat, home to trillions of bacteria that break down cellulose. The langur's body converts the steady supply of fatty acids into glycogen stored in muscles and liver. Glycogen acts as a quick-release energy reserve for powerful jumps. The langur's muscles are biological batteries, with fast twitch fibers providing explosive force and slow twitch fibers, resistant to fatigue, for sustained activities. This muscular endurance is supported by a high density of mitochondria, the microscopic power plants generating ATP that fuels all muscle contractions. The langur's circulatory system rapidly clears metabolic byproducts like lactic acid, preventing buildup of fatigue-inducing substances and allowing sustained high-level performance. The red-legged langur doesn't just move through its environment, it interacts with it. One of the most spectacular tricks is the ricochet, using a vertical vine or sapling as a temporary pivot to change direction mid-flight. Another tactic involves harnessing elastic energy stored in branches. The langur pumps the branch, timing bounces to the branch's natural frequency, building larger oscillations. This clever use of the environment shows intelligence and adaptability, not just a jumping machine, but a problem solver that incorporates physical resources into its movement plan. The rainforests of Borneo are hot and humid, posing significant challenges for an active animal. Every muscular effort generates heat, and overheating is a serious risk. The langur has physiological and behavioral adaptations for thermoregulation, seeking shade during peak heat, spreading limbs to increase surface area, and using evaporative cooling through panting and sweating. This balances their energy budget, conserving resources by resting when activity would be too costly, ensuring performance isn't compromised by thermal stress. The story of the red-legged langur extends beyond Borneo's canopy. It offers us a blueprint for innovation through biomimicry. Imagine robots with the balancing algorithms of the langur's tail, or prosthetic limbs that use elastic tendons like the langur's jump. By studying the physics of this master acrobat, we can learn to build lighter, more efficient, and more agile machines. This remarkable creature is a vibrant thread in the rich tapestry of life, a reminder of the incredible diversity that evolution can produce, filling every possible niche with perfectly adapted life forms. But like so many species, its world is under threat. The rainforests it calls home are shrinking, and its survival depends on our ability to protect these vital ecosystems. Understanding the intricate physics of its life deepens our appreciation for what we stand to lose. Each langur is a masterpiece of biological engineering, and its loss would be an immeasurable tragedy. The red-legged langur has shown us the extraordinary science hidden within the natural world, revealing the physics behind its every graceful movement. The world is full of such wonders, with scientific secrets waiting to be uncovered in the flight of a bird, the crawl of an insect, or the leap of a langur. All we have to do is look closer, with curiosity and a desire to understand. We hope this journey has given you a new perspective on this incredible animal and the invisible forces that shape its life. Throughout our journey, we have dissected the red-legged langur, breaking down its movements into fundamental principles of physics. But to truly appreciate this animal, we must put all those pieces back together. The red-legged langur is not just a collection of clever adaptations. It is a seamless, integrated system where every part works in perfect harmony, creating a symphony of motion greater than the sum of its parts. Consider one final leap. It begins with the eyes judging distance, involves the brain calculating trajectory, then muscles powered by digestive fire convert stored energy into explosive launch. It is a flawless cascade of physics, biology, and instinct. We set out to reveal the hidden physics behind the langur's grace, to replace wonder with understanding. But in doing so, we may have uncovered an even deeper sense of awe. If you found this journey into the world of the red-legged langur as fascinating as we did, please give this video a thumbs up. It really helps our channel reach more people who are curious about the natural world. And to make sure you don't miss our next scientific adventure, be sure to hit that subscribe button and ring the notification bell. We have many more secrets of the animal kingdom to share with you. Thank you for watching, and we'll see you in the next one.